to this tutorial. Welcome to this tutorial on linear programming. Today, we'll walk through a complete example to show you how to solve linear programming problems graphically. We'll cover the 6 key steps: formulating the problem, determining the axes, finding coordinates for constraint lines, representing those constraints graphically, identifying the feasible region, and finally finding the optimal solution. Let's dive into our example problem. A factory makes 2 products, A and B. Each unit of A yields $3 profit, while each unit of B yields $5 profit. Making 1 unit of A requires 1 hour on machine I and 2 hours on machine 2. Making 1 unit of B requires 2 hours on machine I and 1 hour on machine 2. Both machines are available for 8 hours per day. Our goal is to determine how many units of each product to make daily to maximize profit. Let's start with step 1, formulating the linear programming problem. First, we need to identify our decision variables. Let X be the number of units of product A produced per day, and Y be the number of units of product B produced per day. Next, we formulate our objective function. Since we want to maximize profit and each A gives us $3 while each B gives us $5, our objective function is maximize Z equals 3X plus 5Y. Finally, we need to formulate our constraints. For machine I, we have 1x plus 2y is less than or equal to 8. For machine 2, we have 2x plus 1y is less than or equal to 8. And we must include non-negativity constraints: x is greater than or equal to 0 and y is greater than or equal to 0. Moving on to step 2, determining the axes. We'll plot x, the number of units of A, on the horizontal axis, and y, the number of units of B, on the vertical axis. Now, for step 3, finding coordinates for our constraint lines. For our first constraint, 1x plus 2y equals 8, we need to find its intercepts. When y equals 0, x equals 8, giving us the point 8, 0. When x equals 0, 2y equals 8, so y equals 4, giving us 0, 4. For our second constraint, 2x plus 1y equals 8, we follow the same process. When y equals 0, 2x equals 8, so x equals 4, giving us 4, 0. When x equals 0, y equals 8, giving us 0, 8. Now for step 4, representing our constraint lines on the graph. We'll draw the first constraint line through the points 8, 0, and 0, 4, representing x plus 2y equals 8. Then we'll draw the second constraint line through 4, 0, and 0, 8, representing 2x plus y equals 8. Since our constraints are less than or equal to, we shade the half planes below and to the left of these lines. And because of our non-negativity constraints, we only consider the first quadrant where both x and y are non-negative. Step 5, identifying the feasible region. The feasible region is the set of all points that satisfy all our constraints. This is the purple shaded region formed by the intersection of all our half planes. The vertices of this region are at 0, 0, the origin for 0, the x-intercept of the second constraint, 0 for the y-intercept of the first constraint, and the intersection point of our 2 constraint lines. To find this intersection point, we solve the system of equations x plus 2y equals 8 and 2x plus y equals 8. Multiplying the first equation by 2, we get 2x plus 4y equals 16. Subtracting the second equation, 2x plus 4y minus 2x plus y equals 16 minus 8. This simplifies to 3y equals 8, so y equals 8 divided by 3. Substituting back, we get x plus 2 times 8 thirds equals 8, which gives us x equals 8 minus 16 thirds, which equals 8 thirds. So our fourth vertex is at 8 thirds, 8 thirds. Finally, step 6, finding the optimal solution. In linear programming, the optimal solution always occurs at one of the vertices of the feasible region. So we need to evaluate our objective function, z equals 3x plus 5y, at each vertex. At the origin, 0, 0, z equals 3 times 0 plus 5 times 0 equals 0. At 4, 0, z equals 3 times 4 plus 5 times 0 equals 12. At 0, for z equals 3 times 0 plus 5 times 4 equals 20. At 8 thirds, z equals 3 times 8 thirds plus 5 times 8 thirds. That's 8 plus 40 thirds, which equals 64 thirds, or approximately 21.33. Comparing all these values, 0, 12, 20, and 21.33, we see that the maximum profit of $21.33 occurs at the point 8/3, August 3rd. Therefore, to maximize profit, the factory should produce 8/3 units, or about 2.67 units, of product A and 8/3 units of product B per day. Let's summarize what we've learned about solving linear programming problems. We went through 6 steps. First, we formulated the problem by identifying decision variables, creating our objective function, and defining constraints. Second, we determined our axes to prepare for graphing. Third, we found the coordinates for our constraint lines. Fourth, we represented these constraints graphically. Fifth, we identified the feasible region where all constraints are satisfied. And finally, we found the optimal solution by evaluating our objective function at each vertex of the feasible region. Linear programming is a powerful tool used in many real-world applications, from manufacturing to resource allocation. I hope this example has given you a clear understanding of how to solve these problems graphically. Thanks for